All right. Well, hello, everyone. So today I would like to talk about some work that Aaron, Carl, and at this point, a lot of other people and I have been doing on Futures and Tokyo and Async IO over the past few months. And if you look really closely, you'll find a few Back to the Future references during this talk. So, first thing I would like to do is take you a little bit back in time. We'll take about the age of April 2015, right before 1.0 was released. We see this issue on GitHub show up on the RFC repo talking about Async IO. This has been a very hotly debated topic now at this point. There's over 100 comments on this, and you can see this basically throughout the entire ecosystem. Ever since 1.0, this has been a major gap. It's something that Rust is missing. It's one of those major features where it's kind of, I would use this, I would use Rust, I would put Rust to production if it had Async IO. But the story doesn't go here. We can actually go a little bit farther back in time. We can go back to May 30th of 2013, the ancient ages of Rust, where only a few of us are from at this point. And we'll see that this actually spawned off from this issue, this kind of general select and async events. And we can see that this concept of it's not just Async IO, but we have all these events in modern programming systems kind of flying around. And we just want a nice generic way to deal with that. And the solution at this time was actually dated back even farther once we go into Yale 2011. Oh, and you'll also be very impressed with my Photoshop skills throughout this presentation. So if we go back all the way there, we'll see the first commit that added libuv to the Rust repository. This was the heart of libgreen back in the way, way old days of the green threading system that Rust used to have. Now, those of you who have used Rust today are very familiar that we no longer have a green threading system, but this is much to the chagrin of many developers. But this was basically showing that we've been thinking about Async IO, this kind of lots of things flying around from the very beginning of Rust. It's kind of always been a central core guiding value. But at the time we released 1.0 back in 2015, we ended up deciding that we had to ship something, we had to ship a systems language, and we were going to start developing it later. So let's kind of rewind the state back to today, and we'll see around June 30th, I think this is actually the date of the blog post, we had this survey go out. And this survey, one of the questions was, what areas are you working in? Not just in Rust, but what areas do you work in general? And there's a really clear trend here that the top 4 categories here are all very related to the same concept of Async IO or lots of events flying around. So we have web development and servers, which clearly if you want scalable servers, you need Async IO in the modern day and age. For server programming in general, you could have RPCs, you could have database systems, you have microservices. This is kind of the bread and butter of Async IO nowadays. And then even just going down farther, we have front-end apps where you have these events coming in from clicks, from keyboards, from the file system, from all over the place. And we also have network programming, which is also basically the heart of all Async IO. So this is really showing that if we were to solve this problem, if we were to kind of really heads-on tackle this, we're going to impact a major portion of not only the Rust community, but actually the technical community at large. And the great part about this is we're not actually starting from scratch. We have all these great projects to draw from today. So we have Finagle, which is a framework in Scala written by Twitter, which they use to write a lot of microservices. And the key thing there is they have this concept called Futures, which is powering the underlying servers, allowing composition, allowing scalability, and kind of separation of concerns. And all of this is in turn built on Netty, which is the Async IO system of Java. And then you can also start seeing Finagle is also written in C++, kind of inspired in C++ with Facebook's project called Wangle. So we can take all this and we can kind of conclude that one of the best routes to go on with Rust is Futures. Again, awesome Photoshop skills. So the first thing I want to talk about is what actually is a future. If you've never heard of this before, or if you've come from anywhere else, actually lots of people have different definitions of futures. So this is kind of just a placeholder for a value that's going to come out at some point later in time. So this could be a database query where you're fetching a row and you want to actually get the row out. This could be an RPC request where you're sending something saying, I would like to update my row, and it lets you know when you're actually done. It could also just be some ephemeral value, which is not actually something coming at you. So a timeout, just some event happening in the future. You get notified when that happens. But it could also range from CPU-intensive work as well. So you have threads running in some external thread pool. You have something happening concurrently on your own personal thread once you're actually not doing it. And that'll all come in through futures as well. And then we can also go down to the socket layer as well, such as when this socket is readable, or when this socket is writable, or when that write event has completed. All of these can be expressed with a concept of just a simple future. And we can see how futures end up spanning the range of this entire class of applications and allow fusing all of these together in one simple concept. So if we take a look at what it actually is in Rust, you'll find this definition in the futures crate. And the first thing that'll jump out at you is actually the fact that it's a trait. And I'll talk a little bit more about that later, but this ends up being a key aspect of the design of futures themselves. And the next thing you'll see is the item and error types, where all that's really saying is that a future will resolve to some value in the future. So in this case, if you're successful, it'll come out with an item. If you're an error, it'll come out with that particular error. And these are generic, so there's not one kind of error, there's not one kind of item, there's kind of domain-specific, whatever is most appropriate for that application. And then the last thing we'll see is kind of the core method which all features are built on top of. This is kind of the only way to actually pull a value out of a feature is this function called poll. And there's a lot of stuff going on in this function called poll. It's a little more subtle than what you would actually see. But basically, in a nutshell, it says, here's the value if I have it, or I'm not ready. And then the real magic happens by saying, if I'm not ready, I'm going to make sure I'm going to let you know when it actually is ready. So this kind of, it's a kind of a simple concept, but it's, you'll see a little bit later how just this simple idea of pulling a value out, but also not knowing if it's ready yet, can allow us to build up these really large chains of computation and kind of fuse all these systems together. So one of the great things you can do with futures is something very similar to iterators, where you can compose completely arbitrary futures to one another, where all you know about them is you have this function called poll, and that's it. And so the first thing you can do is you can say, let's run a future f, and then we're done. When we're done, we'll take that value that it actually resolved to, we'll generate a new future, and then run something else. So this is similar in just sequential Rust to say, like, let a equals b, and then let c equals some function of a. This is just saying, after one thing, run the next. Well, we can also run two things concurrently, which that's actually very difficult to express in sequential code. You have to start spawning threads or kind of worry about what's actually happening at runtime. But with futures, you can take any two arbitrary futures and say, I want to wait for either one to be finished, and that's it. And then this itself actually returns yet another future. So we're just kind of layering this onion or layering this composition where we can continue using all of these awesome abstractions built on top of all of these really tiny poll functions here and there. And then finally, of course, we can not only wait for one or two features, we can wait for both features. And there's actually an entire suite of combinators on the feature trait itself. I'm not going to show the full list here. It wouldn't quite fit on the slide. But you can kind of think of this as the iterator trait, where whenever you look at that documentation, there's tons of little gadgets and gizmos for you to play around with. And then the last thing that I want to talk about in the futures crate is streams as well. So a feature has the ability to provide one value over time, but sometimes computations are best modeled by a stream of values happening asynchronously. So a great example of this is that when you have a TCP listener that's accepting sockets, that's actually a great version of a stream by saying, over time, I'm going to give you new client connections. It just wasn't all available all at once. So the trait itself is actually a very similar feature. There's these item and error types that are alighted here. And then the only real difference is the fact that instead of returning an item, it returns an option of an item. And that's basically the same thing as iterator. You have some of an item if you have an item, or none if the stream is ended, and you can keep going. And this is actually really powerful by, we can, down here we have an example where we have a stream of requests, this rex variable, and that's just kind of data coming in off the wire. We've parsed it into a bunch of requests, and we have some stream representing that. We can then really easily represent that, well, we now have a function from this request to a future of a response, kind of like plumbing through futures all the way. So we can say, for every request, I want you to and then process the request and then get the result. So this is very similar to what we saw previously with futures and composing them. But the key thing here is that this is happening for every item. And with that simple function, that simple combinator, we've now created a stream of responses. So now all of that logic of what's actually happening, of parsing the request, of sequencing, like once you have the request, doing your entire processing service, which might involve database requests or whatever, it's kind of all encapsulated in this one stream that now you can pull some responses out of, and you might go then serialize to a socket at some point. So the next thing I want to talk about is features are great. They're kind of awesome for composing things together. They can provide a nice framework to talk about, to work with, and to write these asynchronous applications. But it's not really that good if it's not fast. So we can take this bread and butter of Rust, these zero-cost abstractions, and let's see if we can bolt them on top of features as well. Oh, I got to show you my awesome picture. Oh, my awesome picture. Anyway, we'll just go straight to this. Slowly. All right. So to talk about this, of what it actually means to be zero cost, we need to think about what does it actually mean? What is the best thing we can possibly write? So let's say you have just a simple server, you're accepting sockets, you're going to process that in some fashion and then drop the connection. What you're probably going to do is you're going to use Mio off the shelf. That's kind of epoll on Linux, KQ on OS X, IOCP on Windows, the state of asynchronous IO in Rust. You'll have some state machine that for every socket you accept, you'll kind of transition throughout that state machine. And then along the way, you won't necessarily allocate too much. You won't have any synchronization because you're probably just on one thread. And like this is kind of basically how you construct your entire server. It's not the most ergonomic, but that's the fastest thing you can possibly write. And so this gives us a concrete thing to remember of what do features actually need to compile down to. They need to compile down to the state machine. They need to be using MIO under the hood, and they need to be avoiding all these extra costs. They don't need to have any sort of implicit synchronization or implicit allocation. So when I talk about zero-cost features, what I actually mean is all of these kinds of goals by saying there are no allocations in any of the combinators. Select, join, and then, or else then. Every single one you find is all zero cost, no allocations. And at the same time, there's no synchronization in them as well. So whether you're selecting over a database request in RPC, or you're joining over a thread pool computation, or some loading of a database row, there's no synchronization there at the future level. And this actually has a really cool property of meaning that the library itself can go down to no std, which means that libcore can also benefit from all these as well. And I'm actually pretty excited to see how that ecosystem develops around that. And then getting down to what it actually means at the event loop layer means we have just one dynamic dispatch per event. And for an entire connection, there's only one allocation that is imposed the entire time. So this is something that the cost of this kind of comes out in the wash almost entirely by the processing of the request takes far longer than one dynamic dispatch or one allocation. And this is kind of where we can really truly see the zero costness of features and how they all compile down. Now, you've all seen this graph before in the keynote, but I want to show it again because it is really, really cool. We can see this as we go up to implement to see the Rust category, but I want to make sure you look quite like this. This is the reaction you should be having. This is not just Rust, but this is futures. These are the zero-cost features I'm talking about. This is not just, oh, yeah, we're fast. This is, I can't find anything faster than this. This is insane. And so I wanted to talk about how does this actually happen? What features of Rust are we actually leveraging to kind of give us this zero costness and give you this flexibility? And the number one thing that we're using is the fact that it's a trait. And a trait is really, really important in the sense that you can have the most specialized implementation you want. You can write your own impl. You can put your own impl trait on whatever you like. You could use the standard ones, but you get to choose whatever's best for you. And whatever application, if it doesn't quite fit into what all the standard ones do, you can have your own impl and do the very specialized state machine internally. And not only this, but having a trait means that everything is nice and generic. We can plumb that all through so the compiler can see through any sequence of chains of and thens or selects or ors, and it can kind of make sure to have all the intercombinator optimizations. So if one feature doesn't actually produce an error and the compiler can determine that, it can actually eliminate all the branches later on for error handling. And then finally, the traits also give us this great ability to say, sometimes we do want this generic dispatch, sometimes we do want this really fast code, but other times I just want to compile something and I want to compile a nice unit of abstraction, so you have this option of dynamic dispatch as well, this option of packaging it up in a trait object. I want to dive into what one of the function signatures look like. So this is and then from before, which runs the self feature, afterwards runs a closure with the resulting value, and then returns another feature. And the first thing you might notice about this is that it looks a lot like iterator. This means that it's very familiar to you. All of the ergonomics you'll see in the standard library tend to show up with features as well. And we'll see these zero-cost closures. So the fact that F is held generically all the way through to the combinator means that there's no extra allocations for this callback. There's no extra state being held onto here. We can actually compile all that away and kind of monomorphize it all away at compile time. And then not only that, but like the into iterator trait, we also have this easy ability to actually convert into features themselves. So you don't really have to worry about, am I returning a result from this closure, or am I returning a feature from this closure? You can kind of return whatever you want, and it'll automatically get converted for you to have a very nice ergonomic story around this as well. And so the last thing I want to talk about with zero-cost features is we not only have designed them to actually be very fast, but we've also designed them to be very understandable and work very well as they scale up into larger systems. And so this typically comes hand in hand with concerns like back pressure, where when you have a lot of components in a system, but one of them is moving very, very quickly, or one of them is moving very, very slow, you want to make sure that the work doesn't pile up and take down the system because there's not enough memory to buffer up all those requests. So the fact that all features are pull, you have to pull it to actually pull out the value, this means that once you've stopped polling, you're not actually making any progress. So all you have to do is just arrange yourself to stop polling. So it's very easy to apply back pressure to any particular feature and say, all right, you need to not start making progress right now. And not only that, but in these asynchronous systems, there tend to be hundreds of millions of requests flying around. So we have database requests and RPC requests and CPU thread pool requests. And you need a very clear picture of how do I actually cancel one of these? I don't necessarily want it all of them to finish to completion. For example, the TCP connection closed a little bit early. I don't want to do any unnecessary work. So having this concept of to actually make progress, you have to poll a feature. This means to cancel it, you just have to stop calling poll. And that actually really shows up very well in Rust by just using drop. As soon as you've dropped a feature, it's impossible to pull the value out. So it cannot make any more progress, so you've essentially canceled the computation. And then if you have something where it's kind of channels amongst things, you can also say, once I can implement the drop trait specifically and say that, oh, that'll send a signal to the producer and start canceling that, and you kind of propagate that signal upwards. But it kind of fits within Rust idioms, and it's very natural to say, once that's gone away, I no longer have to worry about the value, and it'll kind of all get propagated automatically for you. And then finally, the last thing that helps us scale up features is that those of you who are familiar with epoll know that not only do you get that an event happened, but you get what happened. You get a token saying what actually happened with epoll. And this is kind of crucial to having epoll be high performance. So features can get woken up, but if a feature is waiting on a very large number, like thousands of things to happen, it needs to know why it actually woke up to avoid doing unnecessary work to figure that out. So features also give you all these built-in tools and utilities to ensure that whenever it wakes up, you know exactly why it woke up, and you can basically get the epoll interface, but at any level of a feature. All right, so given all of that background, oh my God, my awesome slides are not showing up. Okay, all right, well, so next thing I'm going to talk about is a framework called Tokio, which we've been using to build up these features, to build up asynchronous I/O with all these features plumbed throughout it. So to talk about what Tokio is, it's a features-powered async I/O stack completely written in Rust that is going to be a one-stop shop for all your async I/O needs in Rust. If you need an event loop, if you need a web server framework, whatever you need, it'll be spanned within Tokio. And at the same time, this is a very layered architecture where there's different entry points depending on what you actually need. So not everyone needs this RPC framework, or not everyone needs multiplexing implementation. You might just need an event loop. And then you'll also see that at the upper layers, we're drawing a lot of inspiration from Finagle, these very successful systems externally to Rust, and we kind of see how to bring all those best of ideas into it ourselves. So to describe what Tokio is what's going on here, at the bottom layer, we have futures, which is the bread and butter of basically everything that's going on. This is how we're expressing all of these asynchronous computations. On top of that, we'll have crates like Tokio Core and Tokio Service, where core is the actual event loop that's happening built on top of Mio, and service is this service abstraction from Finagle, which is allowing a lot of composition at the server level. You can say, my server is simply just a function from a request to a feature of response. On top of these, we can build layers like TLS, SSL. We can build protocol implementations like pipelining and multiplexing. And we can do this in very generic fashions where you don't have to actually, they're not wed to any particular I/O objects here or there. And then finally, on top, we're planning on providing an overarching Tokio crate, which is basically saying the 99% use case of what people want for a asynchronous I/O in Rust will come in this one crate. Everything's all nice and packaged up in one piece for you to go and get running pretty quickly. And one of the coolest things about Tokio is that at all of these layers, we have this concept of middleware as well. So within Tokio Service, we can have middlewares for things like timing out requests, for failing over between servers, for having load balancing, for sending a bunch of requests to servers. This is very much inspired by Finagle, and you'll see a lot of this there as well. But the key idea is that you can kind of slot in at just the Tokio service layer. You don't have to worry about protocols or TLS or what the actual event loop is. You can just work here and have all of these great abstractions and not actually worry about all the implementation details. Other layers are like at the TLS layer, we can not only have TLS, you can have compression like gzip or exe or deflate or whatever you want, serialization like JSON or whatever. And then at the protocol layers, we can have very generic implementations of pipelining or multiplexing. So this means that kind of all these really grungy, nitty-gritty details of writing protocols with these asynchronous I/O parsers have historically been pretty difficult, but you can kind of use these off-the-shelf abstractions to kind of get up to speed running very quickly and have very high-performant implementations as well. And so we have a lot of examples of crates that are using Tokio today. We have a couple of protocols like a line protocol, the Redis protocol. We have a TLS implementation. We have, which is built on native libraries like OpenSSL and secure transport and S-channel and all that. We have a sample socks proxy server, so you can just kind of see all the various pieces of the layer kind of working together and how it might all work out. We have mini HTTP, which you were seeing in the graph earlier. We have an initial hyper client. We have signal handling. We have process handling. We have Unix domain sockets. We have another HTTP client backed by libcurl. So we have a lot of examples to kind of get the ecosystem bootstrapped and up and running, where if you're just kind of interested in how do I actually work with this stuff, how do I actually see what's going on, you can check out any of these repos and kind of see look at the source code, see how it's all interacting, and see how you can get up and running with Tokio and start building it yourself. And so the future kind of, what's coming next? Well, the features in Tokyo Core Crate I just published yesterday on crates.io. And what that actually represents is that we have now reached a level of stability with the features themselves and the actual event loop that it's kind of able to be put on crates.io. It's performant, it's nice and stable. We feel like the interfaces are in a really solid location. And we'll probably still have an 0.2 at some point, but the idea is everyone can start building on top of these as soon as possible. All the other crates like Tokyo Proto, Tokyo Service, all timer implementations, TLS are coming very soon to crates.io as well. We have a little bit of more work to do in terms of stabilizing the APIs and such, and we'll try and get those out as soon as possible. And then in the next near future, we're going to have protocol implementations like HTTP2, which kind of exercise a lot of different portions of an I/O stack and kind of make sure it's nice and battle tested and ready, and also a very performant HTTP client, probably through Hyper at some point. All right, and oh my God, you're missing all my awesome slides. But that was the end of my talk. I have a couple of links here. They have the futures repo, which is under my user, alexcrichton/futures-rs. And then in the Tokyo RS organization on GitHub, you can also find Tokyo itself, which has a very nice README pointing to lots of different projects. And then if you're using IRC, you can find us on Rust internals and Rust and whatever. And if you're using Gitter, you can also find us at a Tokyo RS channel there. Mostly you can go to the Tokyo RS organization on GitHub, and you'll find all the links there. And if you have any questions, I would love to talk more about Async IO right now. Thank you.
All right, so I noticed that the title of your talk is Back to the Futures. So are you a proponent of the multiverse explanation?
I actually recently saw a talk that was describing string theory, so now I'm actually believe that there are 11 dimensions, and so I'm coming around to that fact, yes.
I was wondering how you mapped the Windows IOCP model onto the future model.
Right, this is actually one great part about the Mio library, that if you try and find platform-specific code starting at Tokyo Core going up, you won't find any. And this is where Mio is providing a zero-cost interface that is ePull, so it gives you like the ability to register objects, and you can then pull out events later on. And we have an IOCP backend for Mio, which is basically giving you the readiness model on top of the IOCP model. And the way that works is that internally, kind of whenever you accept a socket, we immediately start a read. And then whenever there's a buffer, we say we're readable, or it's like we're immediately writable. So we do a lot of the buffer management internally at the Mio layer. So it's not a zero-cost implementation over IOCP itself, but it's generally more than performant enough for any form of client. And that's kind of what we've been targeting, is kind of high-performance Linux servers and then kind of clients literally everywhere.
So the first protocol I always love to do is WebSockets, because it's got that lovely upgrade feature. Are there ways within the Tokyo framework to swap out the HTTP with WebSocket, or would I have to have some parent enum that swaps between them, or have you even tried to design those type of things yet?
We haven't quite gotten to the layer of having a WebSocket protocol implementation for sure. And some of the HTTP implementations we've done have been pretty early on, like just parsing off a couple headers and not a lot of streaming bodies and streaming requests. But I think the idea there would be that you would probably use an off-the-shelf HTTP parser that the general HTTP client is using, but then you would very quickly start promoting yourself to WebSocket afterwards. And the idea, a lot of this is still in progress, but we plan to have we're not really imposing sort of buffering strategies if you start going lower down in the stack. And so you can kind of figure out where you want to insert yourself to have as little cost as possible, and ideally not impose any of that going at the upper layers, but still kind of in design to see what happens there.
I'm curious how the poll part of the futures works historically when you look at things like ePull, like you give it a set of things that you have registered and then you call just that one function to pick out whatever's ready. Here on your future trait, you've got a poll method, but if you have like 1,000 of those, like how does that work? You don't have to go super into detail, just kind of.
Right, so the idea is that when you call poll, if it's not ready, it will somehow schedule you to receive an event when you would be ready. And as part of that, what you can do is you can say, you pull out a handle and then you throw it somewhere and then that handle gets notified to kind of let the future go and make progress later. So the implementation detail of this would look like is that when you pull out a handle, it's actually a little extra piece attached to it, which says when this handle gets notified, I'm going to let you know that I specifically got notified versus when that handle gets notified. So what you can end up doing is that internally you have like a list of events that happened, and then when the notifications come in, you start pushing on those events, seeing what actually happened, and then when you get pulled, you just iterate over that list of events and see what happened. So the idea there is that you still don't have to look at everything, you just have a list of things to look at. All right, I think you were next.
I was wondering if you could give us a little bit more details on the relationships or the expectation that you think people should have for building things directly with futures and streams versus using Tokyo services as the abstraction to build into? Like, when would you decide to use one or the other as your kind of layer that you're working with?
Right, so futures are not, like, you would not want a socket to be a literal stream of bytes. Like, that's just, it's the same way that sockets or files are not iterators of bytes. At some levels, like, these abstractions don't quite make sense. So you still have the concept that whenever I read a socket, if it returns not ready, it's kind of future-esque where it'll notify my task when it is ready to make progress. But the key thing here is that we'll tend to have features at all layers of the stack. You can kind of at any point go off and actually implement a feature, kind of convert it to a feature or work with features. But at some intermediate layers, like at the protocol layer, we might literally be using features all the way. And then at the service layer, it kind of depends on whether, are you actually writing a protocol or at the protocol layer? If you're writing a server, you're probably writing this at the service layer, or you're writing various middleware in between there. Is that all making sense?
So you talked a little bit about, you add a bunch of subscriptions or polls, sorry, and you get called back later. What sort of load balancing does it do? Is it just call them all in order? Like, what if I had 10,000 subscriptions? Is the application expected to manage that? Stuff like that.
Right, so this is something, the futures crate itself has no concept of I/O or runtime or polling or anything, or what's actually happening there. So it's very flexible and up to you as a user, kind of how to poll it, how to run a feature, how to compose a bunch of features together. So at that layer, there's not really a question to that because it's kind of, you're the one writing it, so it's whatever you happen to write. But, well,
it's just part of the trait then, it's up to the author to
yes,
okay.
But then as you, like, that tends to be pretty unergonomic because you don't want to always deal with everything all the time. So once you get up to like the Tokyo core layer, you actually have utilities to spawn features. So you're saying like, I want to run this feature on the event loop. I want to run this feature over here. And that just provides a round robin sequence where it says, I'm just going to iterate all the features that are ready, pull them, and then when it's not ready, I'll just turn around the event loop and just do it all again. So you have the ability in the future to kind of yield where you say that I am making a lot of progress, but I'm making too much progress, so I want to let someone else go make progress for a while. And that's kind of a opportunistic thing. It's not done automatically. You'll have to actually opt into yielding at some point.
Okay, so there is still some amount of cooperative multi-processing going on at the library level.
There's no sense of like, we will automatically like context switch you out and put you on another CPU or anything like that. You'll have to have manual points for doing that.
So when you showed the benchmark that was threaded against 8 cores, I believe, where does threading fit into the stack of futures in Tokyo?
That specific benchmark was threaded in the sense that there are 8 event loops, so basically one event loop on every core, and they're totally separate. They're not communicating with each other at all. And so the threading story for Tokyo Core, though, is that there's typically one event loop thread. That event loop is owned by one I/O thread, and then you can have a CPU pool. You can kind of have a thread pool, which is another crate for that, and so you can offload work onto that as well. So the idea is the event loop itself will typically be owned by one thread, and then I/O objects themselves are bound to that. And then if you want to have a multi-threaded server, you tend to have like ways to say share the port, like on Linux with SOE reuse port, or you can have various other kinds of cooperative stuff there. But you have to set it up manually. Like at the Tokyo Core layer, there's actually no thread spawns whatsoever. So you're the one that actually has to go and architect all that. And then once you get to the upper layers, you might have more baked in where it's like one event loop thread and a bunch of worker threads. But that's kind of yet to be designed and being worked out.
What would be the story of futures and coroutine evaluation? Like if I have a protocol, we discussed the chat client. So like if I have a chat client where I process a series of messages and reply with a series of messages, how would I store the local context? Like I assume that there would be like no local stack per future execution or something. Like in Golang, I would just spawn coroutines and would never care. But what would be the story for Rust in this case?
With futures, there's kind of a very strong parallel to things like green threads, or actually threads in general, where they're called tasks. So every feature is pulled as part of an overarching task, and then a task follows this feature throughout its entire lifetime. And that's like that one imposed allocation. So what if you would be spawning Go routines or threads in other systems, what the equivalent would be spawning new features in the future system. So you can kind of have like one task that's driving a bunch of HTTP clients, one task that's driving a bunch of channels, one task that's like servicing all your requests, and then you'd have all those communicating to one another via channels as well. Does that make sense? Awesome.
All right, thank you so much, Alex.
Thank you.
One more round of applause.